All right, welcome back to another lesson in AP Calculus. This is Unit 7, all about integrals and integration. We're going to begin Lesson 3 today. We're going to be discussing antiderivatives and the indefinite integral. So in our last two lessons, we worked on definite integrals. Today we'll learn about indefinite integrals, which are related. So suppose we know that f prime of x is equal to 3x squared. Is it possible for us to determine which function f of x has this derivative? Think about that for a second. See if you can figure out what function, what f of x would have to be in order to have a derivative of 3x squared. So maybe you thought of, well, how about x cubed? Because if I took the derivative of x cubed, I would bring down the 3 and make it 3x to the second power. But did you think about maybe x cubed plus 1? Wouldn't that also have a derivative of 3x squared? Or how about f of x equals x cubed plus e, Euler's number? Any constant at all would work there, right? Because whenever you take the derivative of constant, it just goes away. So f of x is called the antiderivative of f prime. The symbol, the integral of g of x dx, is the indefinite integral of g. So if you see this symbol followed by g of x, that little s symbol, then you mean indefinite integral. The term antiderivative, that is to take a derivative backwards, is the same as indefinite integral. So now we can discuss some formulas for the antiderivative. Yes, you have to learn some formulas, but I hope you see that they're really just undoing the formulas that you worked so hard to learn earlier. So in order to show that, I want us to look at our integration rules right next to the derivative rules. And remember that an indefinite integral means to take the antiderivative. It's just they're synonyms, okay? So we know that we have a power rule. That's this first one here is the power rule. And it says that when you have the derivative of some power, some base u to the n, you bring down the n, subtract 1, and multiply by u prime. Well, we're going to say that the integral of u to the n then is to increase the exponent by 1 and divide by the new one. So if we have like x cubed, when we integrate that, it becomes x to the fourth. I always write that power first and then divide by the new one. Just one little caveat: if you have something that's like a fraction, like maybe we have the integral of x to the 1/2, then you're going to get x to the 1/2 plus 1 is 3/2. And what I say is multiply by the reciprocal. So you'll hear me say increase the exponent by 1, divide by the new one, or increase the exponent by 1 and multiply by the reciprocal of the new exponent. All right, we know that the derivative of sine is cosine, but here you can see the integral of cosine is sine. So everything we saw with derivatives in trig, let's just look at all the derivatives for a second for the trig. You'll notice that all the derivatives of your cos have negative in it. Derivative of co, negative sine. Derivative of cotangent, negative cosecant squared. Derivative of cosecant, negative cosecant cotangent. And that's kind of how I try and get you to learn them and remember them, that anytime you take derivative of a co, there'll be a negative. Well, now it's going to be a little bit different. With integrals, instead of integrating a co that has a negative, it's anytime you get co as an answer, it needs a negative. So the integral of cosine is just sine because the derivative of sine is just cosine. We don't need a negative. But when you integrate sine, it is negative cosine because you got co as an answer. That's what I always say. Even every time you integrate, if you get co in the antiderivative, make sure you have a negative. So you can see our integral of secant squared is just tangent, but our integral of cosecant squared is negative cotangent. The integral of secant tangent is just secant because the derivative of secant is secant tangent. But the integral of cosecant cotangent is negative cosecant because we have a co in the result. All right, we have some properties of the indefinite integral, and these should look familiar to you from the properties of the definite integral. In case you're wondering, the difference is indefinite integrals don't have anything written here, right? So if you see the integral from 3 to 5 of f of x, we know that we're talking about the definite integral. That's that area, that signed area between the curve and the x-axis. If they don't have numbers there, we're talking about the indefinite integral or the antiderivative. You can see we can split them across from addition and subtraction, but we cannot, that's saying not equals, we cannot separate multiplication and division. Does not work. Okay. We can still pull out constants though, and so that's nice. All right, let's work some example problems. I'll start with the integral of x to the 5th dx. All right, what does that equal? That equals x to the 6th over 6 plus a constant. Always got to say plus a constant. And, in AP calculus, forgetting that plus c for the most part, you might think, oh, it's just not important. Maybe teacher take off 1 point. Well, the further you go in calculus, the more that c can really mess you up if you forget it. Because problems that have multi-steps, and we'll see some of them, that c becomes something super important because it becomes more than just a constant. More on that later. Okay, let's take a look at the next one. First, let's rewrite this integral with negative exponents. We usually like negative exponents in calculus. That's x to the negative 4th. So I add 1 to the exponent to become negative 3 over the new exponent, which is a negative 3 plus c. All right, let's integrate this. Notice I've got t's and I'm integrating with respect to t. This dt, dx, super important. Without it, the indefinite integral makes no sense. We'll learn more about what that means later. You've seen it already with differentials, but I want you to just think of it for now as telling you what letter to integrate with respect to. I'm integrating with respect to t. So I need to increase my exponent on t, divide by the new one. Increase my exponent on t, divide by the new one. What about 6? What happens to it? Well, that's 6t to the 0, so it becomes 6t to the 1st. And then don't forget your constant plus c. Looks like we could clean this up a little bit if we wanted to, reduce the 3 and the 4 over 2, but I'll just leave it like that for now. All right, go ahead and do these practice problems, please. Okay, let's see how we did. This first one, we want to rewrite this as x to the 1/2. We prefer fractional exponents and negative exponents because they make the power rule easier. So 1/2 plus 1 is 1/2 plus 2/2, which is 3/2. Then I'm going to multiply by the reciprocal. So instead of dividing by 3/2, multiply by 2/3. And then plus c. Don't forget your plus c. All right, so we're just going to do this one at a time. X to the 4th over 4 minus 3x to the 3rd over 3 plus x to the 2nd over 2 minus x to the 1st plus c. Okay, the integral of sine of theta d theta. So we're integrating with respect to theta. So theta is like our x. That's what that's telling us. We know that the integral of sine is cosine of theta, but because we got a co in the answer, that reminds me to make it negative plus c. All right, let's go down and take a look at some of these. All right, secant squared minus cotangent x cosecant x. Oh my goodness, on 2 of these I have done the bad. I have forgotten my dx. I can be sloppy about that. It doesn't make any sense if you don't have the dx. But I get lazy sometimes. That's bad. I shouldn't do that. All right, let's integrate this one. Secant squared x, the integral of secant squared x. Well, what has a derivative of secant squared? Well, that's tangent. So this becomes tangent of x. And then what has a derivative of cotangent cosecant? Well, it's not the way I usually remember it. I usually think it was cosecant cotangent, right? It's like secant tangent, but the co, so it must be cosecant. So this is cosecant x. But remember, if you get a co in the answer, it's negative, which makes that a plus. And then plus c. All right, well, there is no product rule in integrals, so what we have to do is we have to expand this. 2x squared plus 6x minus 1x is plus 5x, and then minus 3 dx. Now I'll integrate, makes this 2x cubed over 3 plus 5x squared over 2 minus 3x plus c. All right, let's do the next one. X to the fifth over x squared is x cubed. Minus 3, x squared over x squared becomes just minus 3. And then plus 2x to the negative 2. So I was able to divide each term because this is a monomial. If it wasn't, it had to do something different. We'll just up each exponent, x to the fourth over 4, minus 3x, plus 2x to the negative 1, divided by a negative 1, will make it a negative 2x, plus c. Okay. An equation containing a derivative, such as f prime, f double prime, or dy dx, is called a differential equation. Differential equation. The art of solving differential equations is a really big part of math. In fact, after a couple of years, 2-3 courses of calculus, usually you go into a course that's dedicated on differential equations because it is so foundational in so many different aspects of applied mathematics. When solving a differential equation, first we find what's called the general solution. So we're going to find a general solution. And then if we have it, if we have an initial condition, it's often called an IVP or initial value problem, then we can find the particular solution. So we can solve for the missing c, in other words. Let's see how that works. Let's solve this differential equation. So we know that f prime of x is equal to 6x squared. Well, what we're going to do is we're going to integrate both sides with respect to x. So we don't usually show all of this work, but we're going to say the integral of f prime dx is equal to the integral of 6x squared dx. Usually I just go straight to what the antiderivative is. But we can see that that's kind of how it would work out algebraically. That's f of x. And the integral of 6x squared is 6x cubed over the new exponent 3 plus some unknown constant c. Since I'm going to be doing more work, I'll go ahead and reduce this to make my life a bit easier. 2x cubed plus c. Now we were told that f of 1 equals negative 3. So I know that I get negative 3 when I plug in 1. And 1 cubed is 1. So I have negative 3 equals 2 plus c. So negative 5 is equal to c. Now I can state the final solution. The particular, this is the general. And here's our particular solution. 2x cubed minus 5. And it's quite often rather remarkable with some of these how big a difference the initial value can make in the total look of the problem when done. All right, let's take a look at practice 3.2. Go ahead and give that one a try. Okay, after you take the antiderivative, you get f of x equals x cubed over 3. The antiderivative of secant squared. What has a derivative of secant squared? Tangent. And then plus c. We know that f of 0 is 2, so that's going to make that 0. The tangent of 0 is 0, so this is just telling me that c is equal to 2. So f of x equals x cubed over 3, or 1/3 x cubed, minus tangent x plus 2. All right, let's go to example 3.4. Now we've got f double prime, so we're going to have to do this process a couple of times. First, the integral of f double prime is just f prime. The integral of cosine is sine. There's no negative because remember, it's only negative if you get co in the answer. All right, f prime of 0 is equal to 3. So, I forgot my plus c. Put a 3 here and put a 0 in for x. Well, the sine of 0 is 0, so this is just telling me that 3 equals c. So now we know that f prime of x is equal to sine of x plus 3. Let's take the integral again. That gives me f of x equals negative cosine of x plus 3x plus c. This time we're told that f of 0 is negative 2. So I'll put a negative 2 in and put 0 in for f. Well, the cosine of 0 is 1, so this is negative 2 equals negative 1 plus c. So negative 1 is c. So our final answer, f of x, is negative cosine x plus 3x minus 1. All right, let's take a look at practice 3.3. A particle moves along the x-axis at a velocity of v of t equals this equation for t greater than or equal to 0. At time t equals 2, its position is x equals 3. Find the particle's acceleration function and then find its position. All right, so let's find the particle's acceleration. Well, acceleration is the derivative of velocity. So acceleration is equal to v prime. So that would be 12t squared minus 6t. Now, to find the position function, we need to remember that velocity is the derivative of position, so position is the antiderivative of velocity. So that becomes 4t to the fourth over 4 minus 3t to the third over 3 plus 5t plus a constant. Isn't that cute how they gave us those perfect little things to just cancel those out? And we know that at time t equals 2, position is 3. So I'll put a 3 there, and I'll put a 2 in for t. 2 to the fourth is 16. 2 to the third is 8 plus 10 plus c. Oh, I don't feel like doing all this math. Let's see here. 26 minus 8 is 18. So I think it's a negative 15. If I'm wrong, don't tell me. S of t is equal to t to the fourth minus t cubed plus 5t minus 15, or thereabouts. All right, let's talk about the next one. Example 3.5. Suppose the acceleration of gravity is a known magnitude of g in the downward direction. Let's write the function for the acceleration of a particle moving along the y-axis in terms of g. So we're saying gravity is some function, some constant g, okay? And the magnitude is g. The downward direction will indicate with a negative. So we know that the acceleration of some particle moving along the y-axis has this acceleration of negative g, and that's it. The acceleration under gravity is constant. So let's assume that the particle had an initial velocity of what we call v naught. That is, that v sub 0 is equal to the velocity at time t equals 0. Let's find the velocity function of the particle. Well, the velocity is the antiderivative of acceleration. So velocity is equal to negative g times t. I'll use t here. And then plus some constant, right? But we know that v of 0 is equal to v naught. So v naught is equal to negative g times 0. That's just 0 plus c. So it turns out this c is my v naught. So we get that velocity is equal to negative g of t plus v naught. Assume the particle had initial position of y naught. Can we find the position function? Well, sure. We just integrate this. S of t is equal to negative g t squared over 2 plus v naught t plus a constant c. But we know that when you plug in 0 for t, all that goes away, and it's supposed to equal y naught. So instead of saying c, I'll just say y naught. And this is the process that Sir Isaac Newton went through to get that wonderful position equation for a particle in a vacuum under a constant gravity. So as you can see, it makes it to where all you need to know is gravity and your calculus, and you can get any equations that you need. And it looks like that is it for this lesson. So I'll see you in the next one.